Hello everybody and welcome to Lab 10 where we're going to be talking about the SIR model of a disease. Now this lab is going to be pretty relevant to our current situation, so I'm going to be going over the full discussion so you can sort of get a better understanding of how this all works. So the SIR model is a mathematical model of the spread of an infectious disease satisfying the following assumptions: that 1. The disease is short-lived and rarely fatal; 2. The disease is spread by contact between individuals; and 3. Individuals who recover develop immunity. So we're going to set three functions, S of t, I of t, and R of t, to represent the number of susceptible people, infected people, and recovered people from the disease. So the system of equations, or the system of differential equations, satisfies the change in susceptible people is equal to minus ASI. This di dt is going to be equal to ASI minus BI, and dr dt is going to equal to BI, where A and B are constants, and S and I are going to represent these functions S and I. Now, how does this work? So we're going to assume that since the disease is spread by contact between individuals, that some constant factor of interactions between susceptible and infected people is going to be the rate of change of susceptible people, because once you're infected, then your number is taken away from the people who are still susceptible to the disease. The change in infected people is, of course, the increase in susceptible people who get infected by the disease, minus some constant of the people who are infected that recover. So, so the disease is short-lived, and individuals who recover develop immunity. So we're going to take some proportional factor of infected people are going to recover over some time period. And finally, the change in recovered people is simply the people who recover, which is, as you can see, sort of balances out the negative change in infected people. So because the total population n, so we're going to just call like the number of people in the population n, it remains constant over a short time period. So we know that n is equal to s over t, s of t plus I of t plus r of t, and we can rearrange this and show that r of t is equal to n minus s of t plus I of t. So this means that we don't really care about this term right here because we can always calculate it if we know dsdt and didt. Or sorry, not dsdt, like the values for susceptible and infected. Therefore, we can just take a look at these first two equations, and as it turns out, this is a homogeneous differential equation because, as you can tell, the only variables on here are s and I, and there is no t. So of course, this means that we can use our favorite tools, p-plane and d-field, to graph these. Alright, and so for this assignment, we're going to assume that the total population is 5 million people, that t is measured in months, and that we're measuring the time period from 0 to 4. So for question 1, experimentally, it was determined that for a certain strain of flu spreading through this community that is satisfy the SIR model with A equals 1.1 and B equals 1.3. Initially, that there are 1 million infected and that there are 3 million who do not have nor have ever had this particular flu virus. So this means that there are 3 million susceptible. So for part A, we're going to use p-plane to plot the phase portrait with the values A and B and the initial conditions as above. So again, this should be pretty familiar to you guys. We just have s prime is equal to negative a times s times I, and I prime is equal to a times s times I minus b times I. And I've specified these parameters down here. So if we graph the phase plane, it should look like this. And for our initial condition, we have 3 million initially susceptible and 1 million initially infected. And our computation interval is going to be from 0 to 4. So press solve. We should see this. So print out your plot and describe in words what is happening to S and I as time t progresses from 0 to 4 months. So as you can see here, on the s-axis right here, we see that S is continually decreasing, right? This means that S is getting lower and lower as time goes. Even though the infected people starts off rising, eventually at some point they don't. The infected population, I guess, starts decreasing. Now for part B, from your graphs and the various graphing options in p-plane, approximate the maximum number of infected people during the first 4 months, and estimate when this occurs. So we could just zoom in here and get our answer for like the maximum infected, but we also need to know when it occurs. So we're going to have to go and plot y versus t, right? Because infected is on the y-axis, so we choose y versus t. And we choose this solution curve. So as you can see, we have this little graph here. We might crop it a little bit to see right here, and at the top it seems like it's about 1.72-ish. And this occurs around t equals 0.58 months. Now, for part C, is the number of susceptibles ever the same as the number of infected people in this time interval? Okay, again, we can do the exact same thing. Use this these S and I of t versus time graph. So we just choose both over here, and here we can see at this time period right here, the number of susceptible people and the number of infected people is the same. So to again find exactly when this occurs, we can crop it really close and find that it's about 0.4. And if we restore it, we actually find that there's a second point right over here where the susceptibles equals infected. And if we crop it like this, we can see that this other intersection appears around 3.32 months. Now, for part D, estimate S of 2, I of 2, and I of 3. These values will be used in the next part. So again, we can go back here. So we want to estimate S of 2 and I of 2. So here, let's just crop it around time equals 2 months. And find that S of 2 is about 0.2, maybe like 0.19 maybe. And here we see that it's about 0.55, I guess, maybe 0.56 probably. And for I of 3, we can zoom in a little closer right here. Oh, whoops, that's too close of a time interval, so it screwed up. There we go. We see that I is right about maybe 0.18 million people. Alright, so for question 2, suppose that at time equals 2, the flu virus mutates so that the value of A changes to 0.5. Estimate I, the number of infected 1 month after the virus mutates, and compare this to the value of I of 3 from above and explain the difference. So we're just going to change our value of A right here to 0.5. Graph this phase plane, go get our keyboard input of initial value, and if you recall, we estimated that S at time equals 2 was 0.19, and the infected at time equals 2 was 0.56 or 55. It doesn't really matter which one. And if we press solve, we will see that we have this little segment right here. So to estimate again, we're going to find the infected people at time equals 1 now. Remember, 1 month afterwards. So about 1 month afterwards, let's crop this again to get a better look at it. About 1 month afterwards, we see around 0.165, right? So if you remember in our original graph, at time equals 3, the number of infected was about 0.18. So this is a bit lower actually than what we had originally, and well, why would this be? Well, if you think about it, what does A represent? A represents like sort of this constant for how quickly it infects people, right? So if this A is higher, then there's a higher likelihood that the susceptible people would be infected, and this if A is lower, like what just happened, it gets lower, then the likelihood that people get infected is lower. And so this means that we should see less infected people, and comparing the values 0.18 to 0.165, we can see that this is indeed true. All right, so for number 3, local officials will consider various strains of the flu an epidemic when the number of infected reaches a maximum. So using this model in p-plane with the values shown in the tables below, estimate the values of t at the time t star where the number of infected is a maximum. So we're going to use the values. First off, A equals 1.5 and B equals 3. So if we graph this here, and our initial condition 3 and 2, and let's solve it, what do we see? Okay, so this actually goes a little bit off of the graph, so I'm going to change it a little bit, change the minimum s to -1, minimum I to -1, and the maximums to 5, just so I can see it better. There we go. Okay. So again, if we take a look at the graph for this, we want to take a look at S when the number of infected is a maximum, right? So the max I is like somewhere in this interval. So if we crop it, we will see that maybe the maximum occurs around here, where S happens to equal 2. So if we write that down, cool. Now let's try to plot it. So let's erase this solution. Now let's try to plot it with the initial condition 3, 1.1. Okay, graph the x or s versus t and I versus t. And when I is maximum, like right about here, oh, we should see that s equals 2 as well. And you should find that they are actually all 2. Let's try once more with the last example just to make sure. So going to erase this solution and graph with initial condition 2, 3. And again, if we take a look at these graphs, well, the number of infected maximum is just at 2, is just like at time equals 0. And, well, the initial condition was s equals 2, and we see that, again, we find that when the number of infected is maximum, s equals 2. Okay, this is interesting. Let's try again with different values of A and B. So we're going to change the value of A here to 2 and graph this phase plane. And we're going to use the same initial conditions. So s equals 3, I equals 2, solve, graph, and we should find that when number of infected is at a maximum, like right around here, looking down, we see that s is equal to 1.5. And, well, you should see a similar pattern if you graph out all of these other points. I'm not going to graph them, but I'm going to encourage you to graph them. But you should see that they also, when time is at the time when the number of infected is maximum, the number susceptible is equal to 1.5 million. So for this system, explain why you should expect that I of t reaches a maximum when S of t star is equal to b over a. Do the results in your tables provide numerical evidence for the above statement? Well, obviously, if we take a look at the numbers, b is equal to 3, a is equal to 1.5, 3 divided by 1.5 is 2. And we did see that this number susceptible at the maximum infected was indeed 2. Again, b equals 3, a equals 2, 3 over 2 is 1.5, and we see that number susceptible was indeed maximum there. Now, why do we expect this to be true? Well, we should see a maximum when di dt is equal to 0, right? And recall that di dt is equal to asi minus bi. So, dividing both sides by I, we get that 0 is equal to as minus b. b is equal to as. And therefore, at the time when di is equal to 0, di dt is equal to 0, we get that s is equal to b over a. So this also gives us some mathematical proof for this fact that we have just shown. Alright, so for number 4, it is sometimes of interest to rescale or normalize the quantities s, I, and r in the model. If n is the total population, let little s be big S over n, little I equals big I over n, and little r equals big R over n. So what is s plus I plus r? Well, we know that big S plus big I plus big R is equal to n, like the total population. This means that divide the entire thing by n, little s plus little I plus little r should just equal 1. And this would be a proportion. We have normalized it, and therefore little s, little I, and little r now represent proportions of the population that are susceptible, infected, and recovered. So for part A, derive the corresponding system for the new variables s, I, and r. Alright. So originally we had, let's see here, ds dt is equal to negative asi. We had d big I dt is equal to asi minus b big I. And d big R dt is equal to bi. Okay, so now all we have to do is to replace all of these quantities with their respective counterparts. So big S is equal to little s times n, right? Because given that little s is equal to big S times over n, we know that big S is equal to little s times n. So we could just replace all these quantities, right? So dsn dt is equal to negative a sn in, right? And factoring out the n over here gets us dn times ds dt is equal to negative n squared asi. And taking out an n on both sides gets us ds dt is equal to negative asin. And we can do similar like reductions for the other sides. I'm not going to show all the work here, but I'll have you know that d little I dt should equal asin minus b little I, and dr dt is equal to bi. So even though I'm not showing the work here on your labs, you are still expected to show the work to derive this new system. Okay, now on to part B. An unnamed source in the local government made several statements to the press concerning the strain of flu modeled by the system with A equals 1.1, B equals 1.3, and N equals 5. Your job is to use p-plane to determine whether his statements are accurate. So immediately we see these percentages right here in these statements. And this indicates to us that we should be using the normalized variables in order to more easily visualize these percentages. So if we just head over to p-plane, we can change our system of equations to match what we had, or match our normalized versions. So first, we are going to have little s is equal to a times little I times, little s times little I times n. And little I is equal to a times little s times little I times n minus b times little I. So we should have a equals 1.1, b equals 1.3, and n equals 5. Cool. So starting with statement 1. If initially half the population is susceptible, but only 10% of the population is infected, then there will never be more than 15% of the population infected. Alright, so again, we can just enter in these percentages as values, right? So initially half the population is susceptible, which means that 0.5, right? 50% of the population is initially susceptible. Initially, 10% of the population is infected, and we solve. We see it right here. Oh, that's a good point. I should probably change the bounds here so that we can get a clearer picture. Right. Okay. So if initially half the population is susceptible, but only 10% of the population is infected, then there will never be more than 15% of the population infected. Okay, so let's look at this claim and see if it's true. So we want to see how many people are infected. So we look at y versus t, or I versus t. Click on this orbit, and quite obviously we see that there is a part of the curve above 15%. So this first claim is false. Because this graph tells us that at times between like maybe 0.5 months and 1.5 months, yes, there are times where more than 15% of the population is infected. Now for statement 2. If initially 25% of the population is infected and 25% is susceptible, then the number of susceptibles is never again the same as the number of infected. Okay, so similar to this previous question, we just set these initial conditions to what the claim says, 0.25, 0.25, and let's try it out. So again, we're going to use both x of t and y of t here because we want to compare the number of susceptible to the number of, or the percentage of susceptible to the percentage of infected. And we see right here that the curves intersect, meaning that at some point in the future, the number of susceptibles will equal the number of infected, and so statement 2 is going to be false as well. Now for statement 3. If initially there are no individuals with immunity and the number of susceptible and infected is the same, then after 1 month, at least 50% of the population will be in the recovered group. Okay, so again, initially there's no individuals with immunity and the number of susceptible and infected is the same. So none recovered, which means that 0% of the people are recovered, and number susceptible and infected the same. So we have s plus I plus 0 is equal to 1, and so we get s is equal to 0.5, and I is equal to 0.5. This means that half of the population is susceptible and half of the population is infected. Let's graph this. Let me clear that just to make sure I'm using the right one. Okay, this one. So we want to find after 1 month at least 50% of the population will be in the recovered group. Okay, so recall that um, from our previous equation here, or our previous calculation here, we have that s plus I plus r is equal to 1. So we can calculate r by looking at our values of s and I. Right, so if we look at here, after 1 month right here, right, the number of susceptible is maybe around 0.4. 0.04. Number of infected is around maybe 0.33. So 0.33 plus 0.04 is approximately 0.37, and therefore the number of recovered is the proportion of recovered is approximately 0.63, if my mental math is correct. 0.63 means 63% of the population is recovered after 1 month. Now, our statement was that after 1 month, at least 50% of the population will be in the recovered group. This is true because after 1 month, we see that approximately 67% of the population will be in the recovered group. And finally, question 5 is a little bit more about the mathy side of the SIR model. So A, using the system, show that dsdi is equal to this fraction. Well, it shouldn't be too hard, right? We know that ds di is equal to ds dt over di dt, which is equal to just negative asi over asi minus bi, and taking this negative out of the top, we get asi is equal to bi minus asi, which should agree with our fraction here, asi over bi minus asi. Now for part B, if I of 0 is equal to I naught and S of 0 is equal to S naught, show that I of t is equal to this big equation, I guess, over here. So what we can do is actually use our previously derived equation, right? We have ds di is equal to asi over bi minus asi. And notice that the i's all cancel out, so we get this is as over b minus as. Okay, so this is actually a separable differential equation. Move all the s's onto one side and all the i's onto one side. We should get, maybe let's integrate from 0 to t, right? Some over time, right? So we get the integral of b minus as over as ds, right? Integrating from 0 to t, this is ds, so s of 0 and s of t is equal to I of 0 and I of t di. Right? And since we know that we know the value, we are given that s of 0 and I of 0 are just s naught and I naught. So if we rewrite this in terms of that, okay, so we can take this, simplify this side a little bit, right? We get integral from s naught to s of t of b over as minus 1 ds, right? And if we integrate this side, we get b over a natural log of s plus, or not plus, sorry, minus s from s naught to s of t. And if we integrate this side right here, we should get just I from I naught to I of t. And these are equal to each other. So setting these equal to each other, we get that I of t minus I naught is equal to, and we just substitute everything in, b over a natural log s of t minus s of t minus b over a natural log s naught plus s naught. And we can rearrange this a little bit, right? So we get this I of t, moving this this I naught over to the other side, is equal to I naught plus s naught minus s of t plus b over a natural log s of t minus natural log s naught, right? So this is just a little simplification. And by log rules, we can actually simplify this even further. So I of t is equal to I naught plus s naught minus s of t plus b over a natural log of s of t over s naught. And you should see that this final equation is in fact identical to what we need to show. So we have found our answer. And well, that should be the end of the lab. If you've gotten this far, thank you for watching. Remember that this lab is going to be due next Tuesday before midnight. And remember to stay safe amidst all this, coronavirus crisis. Wash your hands frequently. Don't touch your face. Interestingly enough, a bunch of math YouTubers have actually made videos concerning the coronavirus, and a few of them actually introduce the SIR model and do some simulations with it as well. So I highly recommend you check those out. I'm going to link a few of those in both the description of this video and on Blackboard. If you have some time, it won't be graded, but it's definitely interesting to go and look at some simulations of how this SIR model might actually be put into place, or some other models for how a disease could be, modeled. But other than that, good luck on the lab, and I'll see you next week.